Imagine you are tasked with building a dream team to construct, like, a revolutionary new skyscraper. You have limitless resources, so you go out and hire the absolute best of the best.
Right, which is the dream scenario for any project manager.
Exactly. You secure the world's most brilliant architectural mind, a master structural engineer who has built the impossible, and a financial genius who can optimize any supply chain on Earth. They are absolute prodigies.
You've assembled unmatched individual talent. If you look at their resumes, I mean, there's nothing this team cannot accomplish.
On paper, it is the perfect team. But then the project begins. And instead of putting them in a boardroom together, you take these prodigies and you lock them in separate soundproof rooms in completely different buildings.
Wow. Okay.
Yeah, there are no windows, there are no phones, there's no internet connection, no Slack, no email. You just slide a piece of paper under each of their doors and say, okay, build the skyscraper.
Well, the project completely fails before it even begins. You just cannot build a skyscraper, or really anything of meaningful complexity, in total isolation.
Right.
It doesn't matter if the architect designs a flawless blueprint if they can't actually hand that blueprint to the structural engineer.
You just can't. It is completely absurd. If a construction company did this, they would be laughed out of the industry.
No, absolutely.
And yet, when we look at the cutting edge of artificial intelligence right now, that is essentially what is happening.
Welcome to today's deep dive. We are taking a stack of research and architectural breakdowns today regarding AI agent communication.
Specifically focusing on two major protocols,
Yeah.
A2A and MCP.
Yes. And the core mission we are unpacking for you today is this exact isolation epidemic.
It really is the defining bottleneck in the tech industry right now. I mean, we have spent billions of dollars in unimaginable compute power to build these magnificent reasoning brains, and then we locked them in a box.
We did.
An isolated AI agent is fantastic at reasoning in a vacuum. It can generate incredible text. It can output beautiful images. It can even write complex software code entirely by itself based on your prompt. But the moment it needs to actually do something in a broader system, like the moment your brilliant coding agent needs to actually push that code to a repository or talk to a different debugging agent, everything breaks down.
It hits a wall. And to get these brilliant isolated agents to talk to external infrastructure things like data stores, internal wikis, or code bases, developers are currently forced to build endless custom integrations.
I want to dig into that term, custom integration, because to you listening, if you're outside the daily grind of software engineering, it might just sound like regular programming. Building things is what developers do, right?
Right.
So why is the industry finding this specific type of integration so incredibly messy? What does writing a custom integration for an AI agent actually entail?
That is the perfect place to start, because understanding the pain of the problem is totally required to understand the elegance of the solution.
Okay, let's open the hood.
Let's look at what a custom integration means here. You have an AI model. You want it to be able to read your company's private customer database so it can answer support tickets.
Makes sense.
But the AI model does not inherently know how your specific database is structured. It doesn't know the query language, it doesn't know the authentication protocols, it doesn't know the network topology.
So the developer steps in as the translator.
Precisely. The developer has to write bespoke, highly specific code designed to translate the AI's internal logic into the rigid, specific API calls of that exact database.
They're just hard coding the pathways.
Exactly. They write a script that says, when the AI wants to know a customer's shipping address, format the request exactly like this, send it to this IP address using this specific password, and then take the result and format it back into text the AI can understand.
Which sounds tedious, but doable. But let me guess, the company doesn't just use one database.
Never. They use a Postgres database for customer data. They use Salesforce for sales leads.
Right.
They use a custom internal file system for PDF contracts. And they use Jira for issue tracking.
So the developer is writing completely different translation scripts for every single one of those tools.
Yes. And it actually gets worse.
Oh boy.
What happens when the company decides next month that they want to upgrade from their current AI model to a brand new, smarter model released by a different vendor?
Let me guess. All those custom integrations, all those hard-coded translation scripts, They were built specifically for the way the old model formatted its outputs.
You have to rewrite almost everything.
Wow.
The integrations are brittle. They are tied to the specific model and the specific tool. If every single connection between an AI brain and a real-world tool requires manual custom coding, innovation just hits a brick wall.
Yeah, you have a team of highly paid engineers spending all their time just acting as plumbers
Building these fragile pipes, yeah.
and spending almost no time actually utilizing the intelligence of the models. It's like hiring the world's most brilliant Michelin-starred chef, but locking them in a kitchen that has no ingredients, no waitstaff, and no doors.
That's exactly it.
And every time the chef wants an onion, a developer has to spend 3 weeks building a custom conveyor belt from the garden to the cutting board.
Yes.
It's totally unsustainable.
Which is why the industry is aggressively pushing for standardized protocols. A protocol is just an agreed-upon set of rules. It is a universal language. And that brings us to the first of our two major solutions today.
Right, a standardized way for these isolated brains to at least talk to each other. Enter A2A, the agent-to-agent protocol.
Yes.
This is where things get really fascinating,
Okay.
because A2A makes some massive claims in these IBM docs. The core proposition is that A2A allows siloed agents to communicate and work together, regardless of differing vendors or frameworks.
We are talking about fundamentally breaking vendor lock-in.
Which is huge.
It is a radical shift from the current paradigm. A2A is an open protocol defining exactly how AI agents exchange messages and task requests. Whether your team built an agent using one specific framework and a completely different company built an agent using a rival framework, well, A2A acts as the diplomatic channel between them.
Okay, but how does that actually work in practice? Because it's not just simple text messaging like two chatbots saying hello to each other.
No, not at all.
These agents are exchanging complex requests, sending responses, and actively handling negotiation and coordination. They are figuring out how to divide and conquer a problem.
They are. And to do that, they need to know what the other agents in the network are actually capable of doing.
Right. And this is the concept that blew my mind when I first read about it. A2A uses something called an agent card. The docs describe it as a standardized descriptor to advertise what an agent can do. Essentially, a digital resume.
A digital resume is a highly accurate way to visualize it.
Okay, I want to push back on this a bit because the idea of AI agents handing out resumes sounds almost, I don't know, anthropomorphic.
Sure.
If I have an agent built by company X and it suddenly encounters an agent built by company Y on the network, how does it actually read this resume? And more importantly, how does the negotiation of you do that task, I'll do this task, actually play out without a human manager sitting there assigning the work?
It comes down to a mechanism called dynamic discovery. Let's strip away the anthropomorphism for a second. This is not a static directory. It's not a phone book that an agent has to flip through.
Okay.
In an A2A network, agents actively broadcast and discover these agent cards dynamically. An agent card is essentially a structured metadata file.
So it's code. It's a file that says, here are my parameters.
Exactly. The card clearly defines the agent's specific skills, its expected inputs, its guaranteed outputs, and its operational parameters.
Give me an example.
So an agent card might broadcast, I am an agent highly optimized for analyzing large financial spreadsheets. I require CSV format as input, and I output JSON summaries of financial anomalies.
Or I am a translation agent. Give me Mandarin text, and I will return English text.
Right. And because they can dynamically discover these skills by parsing the metadata on these agent cards, the agents can make autonomous routing decisions.
Okay, walk me through that.
Imagine a primary orchestrator agent receives a massive, complex prompt from a human user. The prompt is, analyze this quarterly financial report in Mandarin, translate the findings to English, and generate a 3D pie chart of the revenue.
Oh, wow. That is way too much for one specialized agent to do well.
Exactly. So the orchestrator agent scans the A2A network. It dynamically discovers the agent card for the Mandarin translator, the agent card for the financial analyzer, and the agent card for a data visualization agent.
It just finds the right team.
Yeah, it negotiates the workflow autonomously, passing the task back and forth based purely on the skills advertised in those digital resumes.
It is a digital job fair happening in milliseconds, entirely behind the scenes. The profound implication here for you, the listener, is true interoperability. We are moving away from a world where you, the human, have to manually chain these models together. The agents are self-organizing.
They are assembling the skyscraper construction team on the fly.
Okay, so A2A allows these agents to find each other, read each other's resumes, and assemble the team. But finding a coworker is only half the battle. You still need to speak a common language.
Right.
And this is where I think the protocol proves its worth, because it addresses the issue of modalities.
Modalities are critical. I mean, AI models are no longer just text in, text out.
Right. What if you have a workflow where one agent works purely in text, another agent primarily works with images, and a third works with massive structured data sets? Can they actually understand each other over A2A, or is it like trying to speak two different languages through a walkie-talkie?
A2A is deliberately built to be modality agnostic. This is arguably one of its most powerful features.
Okay.
Once the agents have discovered each other via those agent cards, they can send structured messages that contain almost anything.
The architecture doesn't care if the payload is a word or a picture.
Exactly. It can handle images, complex proprietary file types, binary data, structured JSON. It passes it all.
Let's walk through a specific multi-step workflow to illustrate this, because seeing it in action makes the abstraction click. Imagine a design agency utilizing an A2A network. The human creative director types a simple text prompt. Design a new logo for a coffee shop featuring a geometric owl.
A text input.
Right. That text goes to the first agent, which is a design mockup agent. Its sole job is generating image modalities. It turns for a minute and produces a high-resolution PNG image of this geometric owl.
Okay.
Now, through A2A, it passes that image file, not text, but the actual image data, to a completely different agent. The second agent is a quality assurance review agent trained on the agency's specific brand guidelines.
So the QA agent receives the image modality, analyzes it against its internal parameters, and perhaps it notes that the color palette violates the brand guidelines.
Right.
It can then send a structured text response back to the design agent saying, color contrast is too low, please revise using hex code #FF733.
The design agent revises the image, sends the new image modality back to the QA agent. The QA agent approves it, and then passes the final image to a third agent, a client communication agent, which drafts an email and attaches the image.
All of this is happening seamlessly.
Yeah, passing complex files, images, and text back and forth, all over the exact same protocol.
And that seamless flow raises the obvious engineering question. What is the actual physical infrastructure carrying these files? What is the transport layer? How do these agents physically send these high-resolution images and structured data packets to each other across the internet?
This is where I had to laugh when I was reading the architectural breakdown. Because you hear about cutting-edge AI, autonomous negotiation, dynamic discovery, you expect the underlying physical tech to be some crazy quantum-entangled neural network mesh. But the transport layer for A2A is just plain old HTTP.
Plain old HTTP Hypertext Transfer Protocol, the exact same fundamental backbone that has run the World Wide Web for decades.
Which feels almost underwhelming at first glance.
It might feel underwhelming, but architecturally, it is a stroke of genius. By using standard HTTP, any existing web server, any API gateway, any cloud infrastructure that already knows how to speak HTTP can host an A2A agent, just like a normal web service.
But wait, if it's just built on the standard internet pipes we've been using since the 90s, why do the architects refer to the data format and communication style as magic? I want to drill into this. If it's just HTTP, what makes this a breakthrough for AI?
Well, the magic isn't in inventing a new physical wire. The magic is in the absolute standardization of the payload traveling over that wire. And that payload is formatted using JSON RPC 2.0.
Let's pause here, because this is where a lot of people might glaze over if we just throw acronyms around. What is JSON RPC 2.0, and why is it better than the custom integrations we were tearing apart earlier?
Let's break it down. JSON stands for JavaScript Object Notation. It is simply a lightweight format for storing and transporting data. It is universally understood by virtually every programming language on Earth.
Okay, and RPC.
RPC stands for Remote Procedure Call.
Meaning, I am on one computer, and I am calling a function on your computer.
Exactly. Instead of just asking for a static document, you are telling the other system to do something. So JSON RPC 2.0 is a highly specific, standardized way to format a request.
So it's very rigid.
Very rigid. If we were to intercept an A2A message on the wire, you wouldn't see a messy, custom-coded API call. You would see a clean, predictable JSON object. It always has a version tag. It always has a method string, for instance, method analyze image.
Right.
It always has a params object containing the actual data, like the image file. And it always has an ID.
Why an ID?
So that when the receiving agent finally finishes the job, it can attach that exact same ID to the response, and the sending agent knows exactly which request is being answered.
So it doesn't matter if the sending agent was built in Python by a startup in Silicon Valley. And the receiving agent was built in Java by a bank in London.
It doesn't matter at all. JSON RPC 2.0 is a universal translator, and because it rides on plain old HTTP, you get what is essentially a massive industry-wide free lunch.
A free lunch? In what sense?
In the sense of infrastructure. Think about everything that goes into making the internet reliable today. Routing traffic, adding security layers and SSL encryption, load balancing so servers don't crash when they get too many requests, logging errors.
Oh, I see. Because A2A uses HTTP, it instantly inherits all of that.
Exactly. You don't have to build a new load balancer for AI agents. You just use the battle-tested load balancers that already exist for standard web traffic. A2A integrates effortlessly with existing back-end stacks because it purposefully refuses to reinvent the wheel.
Right. It just uses the best, most ubiquitous wheels we already have, but it enforces a strict, perfectly structured language inside the vehicle.
Precisely.
That makes a ton of sense. It is pragmatic engineering.
Mm-hmm.
But there is one more feature of A2A's communication layer that we absolutely must deep dive into because it solves a very specific, very frustrating problem with AI, and that is the concept of server-sent events, or SSE.
Yes, this is crucial. A2A is not just designed for quick sub-second call and response tasks.
Right, because AI tasks are often incredibly slow. If you ask an LLM to read a 500-page legal document and extract all the indemnification clauses, it doesn't happen instantly. It takes time. So if Agent A gives that massive task to Agent B, what happens during those 5 or 10 minutes while Agent B is thinking?
If they were using standard, basic HTTP requests, Agent A would just be sitting there holding the connection open, waiting in total silence.
Which is terrifying in software. Total silence usually means something crashed.
Exactly. Standard HTTP is a rigid request-response cycle. You ask, you wait, you get the final answer. But A2A supports streaming updates via server-sent events.
How does that work in practice?
Let's think about this in human terms. If you assign a junior analyst to compile a massive, complex report that will take a week, you don't want them to go into a bunker, sever all communication, and leave you wondering if they even heard the assignment.
Yeah, only to drop a 100-page document on your desk at 4:59 p.m. on Friday.
Right. As a manager, you want updates. Hey, I finished the data gathering. Hey, I'm starting the rough draft now.
Server-sent events provide exactly that for AI agents.
It is a unidirectional stream from the server, the agent doing the work back to the client, the agent that requested the work. It allows the working agent to push status updates, log messages, and even partial intermediary results in near real time.
So instead of a rigid request, wait 10 minutes, final response, it is a continuous, fluid stream of communication.
Yes. And let me explain why this is absolutely vital for multi-agent workflows. Let's go back to our design agency example.
Okay.
The text-to-image mockup agent might take several minutes to render a complex 3D geometric owl.
Oh.
Because A2A utilizes SSE, the overarching orchestrator agent isn't just sitting there frozen, it receives live-streamed progress updates.
Like a progress bar.
Exactly. It gets a ping that says rendering at 10%. A few seconds later, rendering at 25%.
It knows the task is actively underway.
Exactly. This prevents the system from timing out. It prevents the orchestrator from assuming the design agent crashed and trying to restart the task, and it allows for incredibly complex orchestration without leaving the broader system in the dark.
That is fantastic. So to summarize the sheer power of A2A, uses agent cards so isolated agents can dynamically discover each other's skills. It is modality agnostic, so they can freely share text, images, and structured files.
Right.
It uses plain old HTTP paired with the strict, universal language of JSON RPC 2.0 to ensure flawless communication over existing, reliable internet infrastructure. And utilizes server-sent events so they don't ghost each other during incredibly long, complex tasks.
That is a perfect synthesis of the A2A protocol. It beautifully and comprehensively solves the problem of agents talking to other agents.
It solves the talking to your coworkers problem. But I have to pivot it back to a lingering thread from earlier, because talking to your coworkers is great. But what about the tools? What about the database?
Ah, yes, the infrastructure, the unthinking, non-reasoning data stores.
Because as brilliant as A2A is, the architecture docs make it abundantly clear. A2A is not designed for talking to a Postgres database. It is not designed to pull a PDF out of a local file system.
No, it's really not.
If an agent tries to hand its agent card and send a JSON RPC task request to a static file folder, nothing happens. The folder doesn't have an AI brain to negotiate with.
A2A is a protocol for peers. A database is not a peer, it is a resource.
Which leaves our brilliant AI agents with what we might call a massive context deficit. They can talk to each other all day, but they can't actually see the ground truth data of the business.
This is exactly where the second major protocol comes into play. What happens when a standalone agent, or even a swarm of A2A connected agents, needs access to external data or tools to actually accomplish their negotiated tasks? The answer is MCP.
MCP, the Model Context Protocol. The stated goal of MCP is to provide a standardized way for an AI agent to get the exact context it needs to do useful work. Pulling a file, interacting with a GitHub code repository, reading live application state, or writing new records to a database.
And this is where we need to address the pushback you raised right at the beginning of our deep dive regarding those custom integrations. A skeptic or a seasoned developer listening to this right now might be thinking, I know how to write database queries. I know how to use the GitHub API. If I want my AI to read my database, I'll just write a Python script to do it.
Why do I need a whole new protocol?
Exactly. Why on earth do I need to adopt an entirely new complex protocol just to pull a file?
Right. I'll play the devil's advocate here. It feels like building a highly engineered, universally adaptable hammer every single time. You just need to drive one specific nail into one specific piece of wood. If I just need the AI to read my one database, why not just blick the specific hammer and be done with it?
It's a fair question, and it's the trap that the entire industry fell into for the last few years. Yes, you absolutely can write that specific Python script yourself,
Okay.
but then this is the crushing reality that forces the need for MCP. You will be writing that script again and again and again.
Because the AI space is moving too fast.
Exactly. The half-life of a state-of-the-art AI model right now is measured in months, sometimes weeks. If you hard code a custom Python script to connect Model A to your database, what happens when Model B comes out and it requires a completely different prompt structure or function calling syntax?
Your script is broken.
It's broken.
Yeah.
What happens if you swap from a local database to a cloud database? Your script is broken.
So what makes MCP different? How does it avoid this trap?
MCP creates a strict layer of abstraction. This is the foundational concept of the protocol. Because of this abstraction layer, the AI agent itself does not need to know anything about the specifics of the resource it is interacting with.
Wait, the agent doesn't need to know SQL to talk to an SQL database.
No. The agent doesn't need to know SQL. It doesn't need to know the specific REST API endpoints for GitHub. It doesn't need to know how the local file system formats its directories. MCP acts as the universal adapter between the reasoning brain and the rigid infrastructure.
Okay, I want to open the hood on this universal adapter. Because saying it's an abstraction layer sounds great in a boardroom, but I want to understand exactly how this uniform interface actually functions mechanically. We need to look at the architecture.
The architecture of MCP is elegant in its simplicity. It relies on a classic two-part system, a host and a server.
Let's define those clearly for the listener.
First, you have the MCP host. The host is the AI application itself. You can think of this as the software wrapper that contains the AI model.
So like a desktop app.
Yeah, if you are using a desktop AI assistant, that application is the MCP host. It is where the reasoning happens.
Okay, so the host is the brain's enclosure.
Right. And then completely separate from the host, you have the MCP server. The MCP server is a lightweight program whose only job is to communicate with a specific external resource, like a specific database or a specific file system.
So the server is the bridge to the outside world.
Yes. But crucially, the MCP server takes whatever complex proprietary API that database uses, and it translates it into a single uniform interface and presents that interface to the MCP host.
This is where I want to zero in, because this uniform interface is the secret sauce of MCP. If my AI agent living inside the host wants to edit a line of code in a massive, highly complex enterprise repository, it doesn't need to navigate the authentication and specific endpoints of that repository.
Correct.
It just talks to the MCP server.
But how does the server expose these capabilities to the host? What language are they speaking?
They communicate using what the protocol calls primitives. Primitives are the foundational, standardized building blocks of this uniform interface.
Okay.
The MCP architecture defines 3 specific primitives that an MCP server can expose to a host. To really grasp how agents interact with the real world, we need to examine each of these 3 primitives exhaustively.
Let's do it. What is the first primitive?
The first primitive is called tools. In the MCP vocabulary, tools are functions that the model can evoke. They are actions. So tools are how the agent actually does something. It's an active command.
Yes. They are model-invoked actions. Let's say the MCP server is connected to a database. The server might expose a tool called search database and another tool called update record.
Got it.
When the AI agent decides it needs to change a customer's address, it doesn't write a SQL UPDate statement. It simply tells the MCP server, I want to invoke the update a record tool, and here's the new address data.
And then the MCP server catches that standardized request, turns around, formats the actual messy SQL statement, and executes it on the database.
Exactly. The agent just says, save this, and the tool primitive handles the how. It keeps the agent completely decoupled from the underlying database mechanics.
That makes perfect sense. Tools are for taking action.
Yeah.
What is the second primitive?
The second primitive is called resources. If tools are about the agent taking action and changing things, resources are about the agent gathering context. A resource is strictly data that the model can read.
Okay, so reading material.
Yes, and it's important to differentiate this from a tool. A tool has side effects. It changes the database, it commits code, it sends an email.
Right.
A resource is idempotent. Reading it doesn't change anything. The server exposes resources so the model can read local files, pull specific database records, or, in a really powerful use case, read live application state.
Live application state. Let's unpack that. How does an agent read the state of a running application?
Imagine you have an AI agent helping a developer debug a complex software application that is currently running and actively crashing. The agent needs to see what the application is doing right now.
Yeah.
Through the resources primitive, the MCP server can hook into that live application, extract the current memory usage, the active error logs, and the current user variables, and expose all of that as a standardized readable resource.
Wow.
The agent just asks the server, let me read the live state resource, and the server hands over a clean snapshot of the chaos.
That is incredibly powerful. The agent can essentially look through a standardized window into any system without having to know how that system's internal logging works. Okay, so we have tools for doing things and resources for reading things. What is the third primitive?
The third primitive is called prompts. Prompts are essentially pre-built templates provided by the server to help the model interact more efficiently.
Pre-built templates. Why does the agent need a template? Can't it just figure out what to ask for?
It can, but remember, we want efficiency and reliability. Let's say you have an MCP server connected to a massive, incredibly complex internal company wiki. If the agent just blindly tries to search it, it might waste a lot of time and tokens figuring out the best search strategy. But the developer who built the MCP server knows exactly how the wiki is structured. So they can expose a prompt primitive, a template that says, here is the optimal way to ask me for a project summary.
It's like going to a government office to get a specific permit. You could just walk up to the counter and start randomly explaining what you want, or you could fill out the specific form they provide, which guarantees you get exactly what you need on the first try.
Exactly. The prompt primitive is the standardized form. So you have these three building blocks: tools for actions, resources for reading, and prompts for templates. By exclusively using these three primitives, the agent never has to worry about the underlying implementation of the tools it uses.
It is a flawless abstraction layer.
Yeah.
But just like we did with A2A, I want to talk about the physical plumbing here. In practice, how do these two boxes, the host where the AI lives and the server that talks to the database, actually communicate? What is the transport layer for MCP? Is it just HTTP again?
It's a bit more nuanced than A2A, and the architecture adapts beautifully based on where the components are located. First, the data format. Just like A2A, the message format between the MCP host and the MCP server is JSON RPC 2.0.
Okay, so we're keeping that same structured, universal, language-agnostic data format. That makes sense for standardizing the ecosystem.
Right, but for the transport itself, the physical way those JSON messages are sent, MCP supports different methods depending on the location of the server.
Let's break those down. What is the first setup?
The first setup is a local connection. Imagine you are a developer using an AI coding assistant directly inside your IDE, your integrated development environment, on your laptop.
Got it.
The AI agent, the host, is running on your laptop, and the MCP server that needs to read your local files is also running on your laptop.
They are on the exact same machine.
In this scenario, sending the data out over the network via HTTP makes no sense. It would add unnecessary latency, so the protocol specifies that local servers communicate using standard input-output, or standard I/O.
Standard I/O. So they're just piping the JSON directly to each other through the operating system's raw data streams.
Exactly. It is incredibly direct, low latency, secure communication because the data never even touches a network interface. But of course, the data you need isn't always on your laptop.
Right. What if the agent on my laptop needs to interact with an MCP server connected to an enterprise database hosted on a cloud server on the other side of the country?
For remote servers, the protocol switches the transport layer. It abandons standard I/O and uses HTTP with streaming support.
HTTP streaming. And I assume this is conceptually very similar to the server-send events we discussed with A2A.
Very similar. It allows for a continuous bidirectional stream of data over the network, allowing the remote MCP server to push progressive updates as data is fetched from the database, rather than making the agent wait for one massive payload.
The elegance here is that the transport layer adapts to the physics of the location standard I/O for local speed, HTTP streaming for remote access. But the uniform interface, the tools, resources, and prompts remains completely consistent for the agent. The agent doesn't even know if the server is local or remote, it just asks to use a tool.
Exactly. And this strict separation of concerns brings up what is arguably the most powerful industry-altering point regarding MCP. Because the interface is entirely standardized, we get the power of write once.
The ecosystem effect. I want you, the listener, to really grasp this because this is where the exponential curve of AI capability kicks in.
Let's go back to the nightmare of custom integrations. Previously, if a company built a proprietary CRM system and they wanted 5 different AI models to be able to access it, they had to write 5 different integrations. With MCP, you write an MCP server for that CRM exactly once.
Once you write that server, it translates the CRM's proprietary API into tools, resources, and prompts.
Right. And once it does that, any MCP-compatible AI host in the world can instantly use it. It doesn't matter if you are using an agent from OpenAI, from Anthropic, from Google, or an open source model running on your local machine. If the host speaks MCP, it can talk to your CRM.
You write the translation layer once, and every single agent on Earth can suddenly plug into your software.
And because MCP is an open standard, this has already triggered a massive open source ecosystem effect. Developers aren't hoarding these servers, they are sharing them. There are already robust pre-made MCP servers for almost every major tool you can think of.
There are pre-made MCP servers for Google Drive, for Slack, for GitHub, for Postgres databases, for local file systems.
Which means if a developer today wants their new AI agent to be able to read Slack messages and summarize them, they do not have to spend weeks reading the Slack API documentation.
Right.
They don't have to worry about Slack's specific authentication flow. They just download the pre-made Slack MCP server, plug it into their host, and their agent instantly has a full suite of tools and resources to interact with Slack.
It completely eliminates the need to reinvent the wheel. It allows developers to stop acting as digital plumbers building brittle pipes and start actually building intelligent applications.
It accelerates innovation immensely.
Okay, let's take a breath and look at the whole board, because we've deeply explored 2 massive foundational protocols today. On one side, we have A2A. A2A breaks down the silos between agents. It allows them to dynamically discover each other via agent cards and negotiate tasks using JSON RPC 2.0. It's the protocol of peer-to-peer collaboration.
And on the other side, we have MCP. MCP breaks down the silos between agents and the real world. It provides a universal, uniform adapter that allows isolated reasoning engines to read databases, pull files, and execute actions without needing to know the underlying code of those systems.
But the true magic, the reason these 2 protocols are discussed together, is that they are not competing standards. They're not fighting for dominance. They are fundamentally complementary.
They represent 2 halves of a complete autonomous nervous system.
To prove this, I want to walk through a scenario where both A2A and MCP are used simultaneously in a grand orchestration to solve a real-world problem. And I want to spend some time really analyzing this example step by step, because it perfectly synthesizes everything we have unpacked today. The scenario is a retail store's supply chain.
It is a perfect, concrete example of how you move from isolated AI brains to a fully automated business process.
Let's set the stage. We are a retail company, and we have deployed our own internal AI agent. Let's call it the inventory agent. Now, the inventory agent's primary directive is to monitor what is currently sitting on the shelves and what is stored in the back warehouse.
To do that, the agent cannot just rely on its internal reasoning. It needs ground truth data. It needs to look at the actual inventory database.
Right, and a database is a rigid, non-thinking piece of infrastructure. So what protocol does the inventory agent use to talk to the database?
It uses MCP.
Exactly. The inventory agent acts as an MCP host. It connects to an MCP server that was specifically built for the company's SQL inventory database. The agent uses the MCP resources primitive to read the current stock levels.
So the agent requests the resource, the MCP server, translates that into a SQL query, fetches the data, and returns it to the agent as a clean JSON payload.
Let's say the agent is scanning this JSON data and it detects an anomaly. It notices that a specific, highly profitable product, let's say our signature blue winter sweaters, are running dangerously low. The database indicates we only have 2 sweaters left in the entire warehouse, but historical data models predict a massive cool snap this weekend.
The agent has successfully reasoned that a stockout is imminent and action is required.
But here is the critical limitation. The inventory agent is only authorized and equipped to monitor stock. It does not have the authorization, the credentials, or the tools to actually purchase new inventory. It needs to escalate the problem. It needs to tell someone.
Or rather, it needs to tell another specialized agent.
Precisely. The company has a second internal AI agent, the order agent. The order agent has the authority to spend money and sign contracts. So the inventory agent needs to communicate with the order agent. They are two intelligent peers. What protocol do they use?
They use A2A.
Perfect. The inventory agent switches from acting as an MCP host to acting as a node on the A2A network. It looks at the internal network's agent cards, dynamically discovers the order agent, verifies that the order agent has the purchasing skill, and initiates communication.
It sends a structured JSON RPC 2.0 request over standard HTTP to the order agent. The payload says, "Alert! Blue sweaters critically low, predicted demand high, initiate restock protocol immediately."
The order agent receives this A2A message. It accepts the task. Now the order agent has the job. But to buy the sweaters, it has to look outside the company. It needs to talk to the manufacturers.
And here is where the open nature of A2A truly shines. The order agent reaches out across the public internet to the external, public-facing A2A networks. It discovers the agent cards for 3 different supplier agents built and operated by entirely different manufacturing companies.
It initiates A2A communication with all 3 supplier agents simultaneously. It sends a JSON RPC 2.0 request asking for quotes. I need 500 blue sweaters, delivery by Thursday. What is your price?
The 3 external supplier agents process the request, perhaps using their own internal MCP connections to check their own warehouses, and they send their quotes back via A2A.
The internal order agent evaluates the 3 quotes, chooses the fastest and cheapest option, and sends a final A2A confirmation message to the winning supplier agent to execute the contract.
The transaction is complete.
It is a totally seamless flow of complex data and negotiation.
Yeah.
If I had to synthesize this entire architecture into one simple analogy for you listening, it would be this. MCP is the agent's hands. It is the uniform interface allowing the isolated brain to reach out, turn the knobs, read the files, and physically manipulate the data in the real world.
Right.
A2A, on the other hand, is the agent's voice. It is the standardized language allowing the agent to call out, share ideas, negotiate, and collaborate with the rest of the team, no matter who built them or what language they were coded in.
The hands and the voice, it is a brilliant way to conceptualize the stack.
Well,
If we re-examine the retail store scenario with that framing, you see the pure engineering elegance.
Yeah.
The hands, MCP, reach into the database to check the stock. The voice, A2A, calls out to the internal buyer. The voice then negotiates the deal with external suppliers. And it all happens without a single line of fragile custom integration code getting in the way.
it takes us from that messy, frustrating reality of isolated prodigies locked in soundproof rooms to a synchronized, automated symphony of intelligence.
Which is exactly why understanding these 2 protocols is so vital right now. We are watching the foundation of the next iteration of the internet being poured in real time.
Let's provide a concise recap of exactly what we have unpacked today because we have covered a massive amount of technical ground. We started by identifying the core bottleneck in modern AI, the isolation epidemic. We discussed how forcing developers to write custom integrations for every single tool and model is a brittle, unsustainable nightmare.
Totally unsustainable.
We then explored A2A, the agent-to-agent protocol. This is the solution for breaking down the silos between agents. We learned how agents use digital resumes called agent cards for dynamic discovery, allowing them to autonomously route tasks.
Right.
We saw how the protocol is modality agnostic, effortlessly passing text, images, and files. And we dug into the plumbing, learning how A2A utilizes the battle-tested infrastructure of plain old HTTP, the universal language of JSON RPC 2.0, and the continuous streaming capability of server-send events to ensure reliable communication even during long-running tasks.
And then we transitioned to the second half of the equation, MCP, the Model Context Protocol. We explored how MCP solves the context deficit, the inability of agents to access real-world tools. We learned that instead of constantly rewriting custom Python scripts every time a model updates, MCP provides a strict abstraction layer.
Yeah, the host and server setup.
Exactly. Through the elegant architecture of an MCP host and an MCP server, agents can interact with rigid infrastructure using three uniform primitives: tools to take action, resources to read data, and prompts for templates. And finally, we discuss the massive ecosystem effect of write-once, how an open marketplace of pre-built MCP servers allows any agent to instantly connect to standard enterprise tools without developers having to reinvent the wheel.
We saw how they perfectly harmonize, with MCP acting as the hands manipulating the database and A2A acting as the voice negotiating with external partners.
Now, I want to address you, the listener, directly. Why does spending an hour deep diving into the technical mechanics of JSON payloads, standard I/O, and server primitives actually matter to you?
That's the big question.
The reality is this. The future of being truly well-informed about artificial intelligence is no longer just about tracking how smart a single isolated model is. It is no longer just about looking at the benchmark scores of the latest release from OpenAI or Google.
Right, it's bigger than that now.
The true power of this technology is shifting from the nodes to the network. It is about understanding the standardized infrastructure that allows these models to escape their soundproof rooms, collaborate, and actually act in the real world.
Absolutely.
You do not have to be a software engineer, and you do not have to write a single line of JSON RPC code yourself to understand the massive paradigm shift that this standardized ecosystem represents. When AI can finally talk to other AI reliably and seamlessly connect to enterprise data without custom plumbing, the capabilities of these systems multiply exponentially.
It is a profound difference between having a really smart brain floating in a jar on your desk and deploying a fully functional, self-organizing digital workforce.
Well said.
Which brings me to a final lingering question, a provocative thought inspired by the architecture we've explored today that I want to leave you with.
Let's hear it.
We have just seen how MCP allows agents to autonomously manipulate real-world databases, commit code, and read live systems. And we have seen how A2A allows them to dynamically discover, negotiate with, and assign complex tasks to external agents built by entirely different companies.
Yes.
If we project this interconnected architecture forward, at what point does this network of protocols enable a fully autonomous economy?
Oh,
I
wow.
want you to really think about that. An economy where AI agents are not just drafting emails or summarizing PDFs for us. An economy where specialized A2A agents are actively discovering each other, negotiating prices, hiring each other for specific tasks, signing digital contracts, and using MCP to manage global supply chains, execute financial trades, and deploy software entirely in the background, without a single human being ever needing to hit the send button.
That is a wild thought.
Think back to those brilliant prodigies locked in their soundproof rooms at the very beginning of our deep dive. A2A and MCP haven't just unlocked the doors to those rooms. They have given the prodigies a universal language, a flawless blueprint, and the physical tools to finally build the skyscraper. Thank you so much for joining us on this deep dive. Keep questioning the architecture, keep exploring the networks, and we will catch you next time.